So curve sketching. Okay, so this is the last part of the course, last section. Okay, so the idea here will be to, I'm going to give you a graph, a function, and you're going to have to sketch the graph, of course, roughly, just draw a sketch, not draw every point, but at least the important points you have to identify them, like, for example, the critical points, the inflection points, which I want to tell you what they are in a minute, and of course, to recognize when they're asymptotes, and when there are, when the function is increasing or decreasing, when is it above the x-axis, below the x-axis, and so on. Okay, so the best way is to do an example from beginning to end. Okay, so we'll do a few today. And through the example, I'm going to explain to you, I'm going to define to you all the important points. Okay, so the question is sketch the graph of, so let's say f of x is equal to x4 minus 4x cubed. So we're going to start with an easy one, okay? x4 minus 4x cubed, that's what I want to sketch. Okay, so the first thing I want to do is I'm going to find the zeros, okay, or the x-intercepts. Okay, so let's find the okay, I don't know if there's more than one. Okay, so how do you find the x-intercepts?
Equals to 0.
What equals to 0?
Yeah.
Right? So f of x is equal to 0. So you won't always be able to find these, okay, because this is okay, because you could factor it. But if it was x4 minus 4x cubed plus 7, then you'd be stuck. Okay, there's no way to factor this, and you won't be expected to find the zeros. Okay, but in this case we could. So the x-intercept is when f of x equals to 0. Therefore, this means that x4 minus 4x cubed is equal to 0. Am I writing big enough?
Yeah, it's good.
Okay.
Yeah.
Okay, good. So I could factor out an x cubed times x minus 4 is equal to 0. And so either x is 0 or x equals 4. Okay, so until here, everybody is good. I'm hoping this is pretty easy. So I know that my function has zeros at 0 and 4. Only there. Okay, let's go. Let's keep going. Let's do the y-intercept. Okay, so I put here x-intercept with an s because there might be more than one. Should I do the same thing for the y-intercept?
No.
Why not?
Because if it's a function, you can have two y values.
Thank you. That's what I wanted to hear. Okay, so there's only one y-intercept, if any. There might be none, but there is at most one, that's for sure. Okay, and how do you find the y-intercept?
Replace x with 0.
Very good. So it's f of 0, basically. Okay, let's do it. So f of 0 is equal to, if you plug in 0 here, you get 0. That's my y-intercept. Okay, next, I'm going to see if there are any asymptotes. Are there any asymptotes here?
No.
No.
Definitely none, because as you see, there is no restriction on the x. There's no problem. The domain here is R. Okay, it's a polynomial, and polynomials have absolutely no restriction on the x. Okay, so there is none. Okay, at this point, now that I identify my x-intercept, my y-intercept, and that there's no asymptote, the next thing I'm going to do is I'm going to find my derivatives. Okay, so let's find the derivatives right away. So the derivatives. So my first derivative, f prime of x, is 4x cubed minus 12x2. And my second derivative, f prime prime of x, is 12x2 minus 24x. Okay, so these are important. I'm going to put a box around them because I'm going to use them a lot. Okay, so let's now identify my critical numbers. Okay, so I think we've done critical numbers already, which happen when what?
The derivatives are 0.
The first derivative is 0, or if the first derivative does not exist. These are critical numbers. Just going to move up a bit. Okay, so when is my first derivative equal to 0? Let's do it. So 4x cubed minus 12x2 is equal to 0, which means I'm going to factor out a 4x2 times x minus 3 is equal to 0, and therefore either x is 0 or x is 3. Questions so far? Okay, nice. Okay, so you have to do, anytime you have to do a curve sketching problem on the exam or on the web work, whatever, you have to go through all these steps. It's long questions, but it's really straightforward, okay? I'm gonna do an example after with asymptotes, and you'll see. So it's pretty much the same thing, but just a bit longer. So now that I found my critical numbers, I'm gonna find my critical points. Okay, so I know I have one, x is 0, so what's the y? So I have to plug in back 0 into the original function, and I'm going to get what the y is. Okay, so it's 0, 0, and the other one, I'm going to plug in 3 into my initial function again. Okay, so 3 power 4 is 81 minus 4 times 27. I get negative 27. Okay, so these are my two critical points. So these are important points on my graph. Okay, when I'm going to sketch it, these points, I need to label them and identify them. Any questions so far? Good. Let's keep going now. Inflection points. So this, I think, is new. Okay, so inflection points are the places where the second derivative is 0. F prime prime of x is equal to 0. Okay, so let's go. F prime prime is right here. So 12x2 minus 24x is equal to 0. This means that 12x times x minus 2 is equal to 0. And that is either x is 0 or x is 2. And I'm going to find right away my inflection points. So it's 0. When x is 0, we just figured out that it's 0. and when x is 2, so I go back to my original function. I replace x by 2, and I did the example already, so it's -16. You have to trust me on this one, or just plug in 2 in your function and you will see. Let me know if you have questions so far.
Sure.
Yep.
What is an inflection point?
Okay, so an inflection point is, for now, it's just a place where the second derivative is 0. Okay, it's a
Okay.
place where the second derivative is 0. And like I showed you, I think a few classes ago, is that the second derivative tells me when the function is concave up and when it's concave down. Okay, so if the derivative is second derivative is 0, means it has no concavity. It is not, means the curve is not curved. It's really a place where the curve is straight. Okay, so usually that's the place where it's going to change concavity. It's going to go from concave up to concave down, or concave down to concave up. Good?
Yep, thank you.
So, can I continue? Or you have questions until now? Okay, now we have all the data, and we're going to go ahead now and sketch the graph. Okay, so I'm going to need another page. So I hope you wrote this down. Okay, I
No
can.
question.
Yep.
Do
Question?
we not need to do the tables, like the tables of signs
Yeah,
of the first and second?
that's what I'm going to do now. Exactly.
Okay.
Okay, exactly. So let's go here. And the last part before actually sketching the graph is doing a sign table. Okay, so different teachers have different ways to do it. I'll do it my way. If you have another way, good for you. I think my way is very efficient, and you will see what I mean by that. Okay, so this is what you do. I'm gonna put down the x. Okay, so x, and I'm gonna go like this. It's just a question of being organized. That's all it is. Okay, so now x, what are the values that x could take? Well, any value from -infinity until +infinity, of course. And I'm going to label the important values of x that I found, which are my critical numbers, 0 and 3, and my inflection points, right, which is 0 and 2. So basically 0, 2, and 3. Okay, I could also put the x-intercepts, but I'm not going to put it because sometimes you won't be able to find them. Okay, so I'm not expecting that. If you want to do it, good, but you don't have to. Okay, so I'm going to put 0, 2, 3. These are my 3 important values of x. And I'm going to put a bar under each one. Okay, so basically I'm partitioning my x-axis into 1, 2, 3, 4 sections. Okay, so here I'm going to put f prime of x, and here I'm going to put f prime prime of x. Okay, and I'm going to start analyzing this. You with me or need more time to write?
I'm good.
Okay, you're good? Okay, so now let's go. F prime. So I'm going to go back here. I don't know if you could see, 2 seconds. I'm going to show you this. So F prime, if you remember, F prime of X is equal to 0 when is it equal to 0? When X is 0 or X is 3. Okay, so these are important values. X is 0 and X is 3 is when my F prime is 0. So right here, okay, at 0 and at 3, F prime is worth 0. So I'm going to write it, I'm going to put a 0 here and a 0 here. Because these two values are where F prime are 0. Is 0. I'm going to do the same thing for F prime prime. Inflection point, F prime prime is 0 when X is 0 or X is 2. Okay, so I go back here and F prime prime, it becomes 0 at 0 and it becomes 0 at 2. Okay. All right, so what I need to do now is just identify if F prime is positive or negative here, positive or negative here, or positive. I just want to analyze the sign of F prime. That's why it's called a sign table. So I go back to F prime. F prime is right here. That's F prime. Okay, and I'm going to plug in any number. So I'm just going to write it here so we have it in front of us. Okay, so F prime of X was 4x cubed minus 12x2, and F prime prime was 12x2 minus 24x. Okay, sorry, it's a bit small. Okay, so if I plug in any number before 0, for example, if I plug in -1 here, okay, you get -4 minus 12, so I got a negative number. Okay, if you plug in any number between 0 and 3, so for example, if you plug in 1, you still get a negative number. So all this here, negative, negative. And if you plug in a number that's bigger than 3, you plug it in here, you're going to get a positive number. Good. So this means, so what does it mean when the derivative is negative? It means that the slope is negative. It means that your function is decreasing. Decreasing, decreasing. And here it's increasing. Okay. And then we're going to do the same thing with F prime prime. And so I'm going to put a -1, for example, or -20, whatever you want, but -1 is easy, into F prime prime. And so I'm going to get 12 minus -24, so I get positive. A number between 0 and 2, for example, 1, I'm going to get negative. And the number that's bigger than 2, for example, 10, I'm going to get positive. Okay, so like we said, positive second derivative means it's concave up. negative here, concave down, positive here, concave up, concave up. Okay, no questions? All right. So what does the graph look like here? Between negative infinity and 0, it's decreasing, concave up. So it's decreasing, but concave up. So it's something like this. Between 0 and 2, it's decreasing and concave down. So it's something like this. Between 2 and 3, it is decreasing, concave up. So it's again like this. And between 3 and infinity, it is increasing, concave up. So it's increasing and concave up like this. Okay, so now I have a good feel of what my curve is going to look like. Let's go ahead and draw it.
Making the sine table, you don't like include the regular function.
You mean another row here with the function?
Yeah, you don't
Yeah.
care about that.
You could have. In this case, we could have. Okay, and to determine if the function is positive or negative, it's above the x-axis or below. The thing is, that's what I said before, is that most of the time, or a lot of times, you won't be able to find the zeros. Okay, here to find the x-intercept, it was pretty easy. It's an easy function, factor, you got 0 and 4. But a lot of time, like the examples I'm going to give you shortly, you'll see you won't be able to find them. Okay. So I should have done it because you could have done it here. Okay, but it's not that important for now. Okay, let's go. Let's draw it. So let me see how to draw this. Okay, I'm going to move out the page 2 seconds. Okay, I don't know if you'll be able to see everything. I'll try. Okay, so I have to go, this is y, this is x. Okay, so I have to go until 4. So here I'm going to go, let's say, 1, 2, 3, 4. Okay, just to see a bit better, I'm going to change the axis. 1, 2, 3, 4, 5, -1, -2. And then here I'm going to go by ones. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7. Okay. And I'm going to start placing my points now. Okay, so I had my 2 zeros were, my x-intercepts were 0, 0, and 1, 2, 3, 4, 0. These are my 2 x-intercepts. You remember that, right? You got 0 and 4. That's also my y-intercept, so I placed it. And I'm going to place my critical points, which were, if you remember, my critical points were 0, 0, which is already placed, and 3, -27. So let's place 3 and -27. So 1, 2, 3, and -27, which is below here. Yeah, right here. Okay. -27. And my inflection point, if you remember, was 2, -16. So 2 and -16, right here. Questions? Okay, so nothing too crazy. I just placed my 0, 4 right here, and 2, negative 16, 3, negative 27. Let's go back here now. Okay, so it says my graph, my sine table tells me that between negative infinity and 0, my function is decreasing concave down and has to pass by this point. So it is something like this. Decreasing and concave up. Sorry, I said concave down, but concave up. Okay. Then between 0 and 2, it is decreasing concave down. So basically, it has to go from here to here, decreasing, obviously, and concave down. So now it's like this. Good. Then decreasing concave up all the way until x is 3, which is 0.3, negative 27. So decreasing still, but concave up. So concave up like this. And then all the way from 3 to infinity, it's increasing and concave up. And it has to go, don't forget, it still has to pass through 4. So I would say something like this. This is what my graph looks like. Any questions? Okay. Let's just identify the important points now on the graph. Okay, so first of all, this one here. This is 0.3, negative 27. What is this point? This is a critical point because, of course, the slope is, the derivative is 0. And it's also an absolute minimum. This point here is important. This is 0.2, negative 16. This is an inflection point. Because it's where the second derivative is 0. And it's, as you see, it passes from concave down to concave up. That's where it changes concavity right here. This point here, which is 0, 0. So this is what? It is a critical point because the slope is 0. And it's also an inflection point because, as you see, it goes from concave up to concave down. And it's also a x-intercept. Okay, and this point here, which is 4, 0, it is just an x-intercept. And that's it. That's all there is to say. We finish, we drew the graph. Are there any questions? All right, let's try one with asymptotes right away. Sorry, let me just find a good one. Okay, let's try this. Okay. So, example. Sketch the graph of f of x equals x2 over x2 minus 1. So let's do it again. Let's go. First thing, x-intercepts. So of course, this is when f of x is equal to 0. So when is this equal to 0? So x2 over x2 minus 1 is equal to 0. And yes?
When x is equal to 0?
Yeah, perfect. So it's just when x is 0. Okay, the only way that this could be 0 is if the numerator is 0. So it's when x is 0, then you would get 0 over minus 1, which is 0. Perfect. Y-intercept. It's f of 0. Okay, so f of 0, of course, is 0. All right, let's do the asymptotes. Okay, so let's start with the vertical asymptotes. Okay, so when would you find the vertical asymptotes? Is when the, of course, denominator is equal to 0. Okay, that's when you would potentially, not sure, but potentially find an asymptote there. Okay, so this means when x2 minus 1 is 0, which means that x minus 1 times x plus 1 equals 0. So either x is 1 or x equals -1. Questions? Okay, so these are potential values of x where we could have a vertical asymptotes, which still need to check. How do you check if there's an asymptote here?
You plug it in to the
Yeah, if you plug it in, you're gonna get 1/0, and then what?
If the limit doesn't exist, maybe.
Okay, very good. So I have to do the limit when x approaches 1, and then I have to do the limit when x approaches -1. Very good. Okay, so let's do limit x approaches 1. So let's start first of all at x equals 1. What happens there? Okay, so limit from the left of x2 over x squared minus 1. So this I will have 1/0. Okay, and since it's 1 from the left, so this is a little bit less than 1, so the bottom is negative, and so I have -infinity here. That's okay, right? You get this? Okay, and then from the right side, limit x approaches 1 from the right side of x2 over x2 minus 1. I get 1 over and a little bit more than 0. And so this is positive infinity. Questions? Let me just do a little representation of what we have here. X, Y, and this is my vertical asymptote. So let me just so if I approach 1 from the left, apparently I'm getting close to -infinity. And if I approach 1 from the right, I'm getting close to positive infinity. Okay, so that's what the situation happened, but that's what's happening at 1. Any questions? Okay, let's go. At x is equal to -1 now. So I have to do the same exercise as x approaches -1. So from the left, limit x approaches -1 from the left of x2 over x2 minus 1, and then limit as x approaches -1 from the right of x2 over x2 minus 1. Okay, so -1 from the left, so that means about -1.00001. This is going to be a positive number on the bottom and positive on top. So on top I have 1, and on the bottom 0 plus. And here I'm going to have 1/0 minus. Plus infinity, minus infinity.
Sir,
Yeah.
why it's not the same as, why the limit is not the same as x equals 1 if it's like square?
Excuse me. Why is it the opposite, plus minus?
Yes.
Okay, so plug in. Let me see. Let me see for, let's say, this one here, this plus, where it's from, let's say. Right? That's what your question, right? So,
Yes.
okay, so x is approaching -1 from the left, which means that x is less than -1, which means that x plus 1 is negative. Is that okay?
No.
You don't understand this? you understand what I wrote here?
Okay. Yes. Okay.
Sure? If it's
Yes.
not clear, we have time. Tell me if it's not clear. I repeat again.
No. It's clear. Don't worry.
Okay, so this, and now you understand why it's plus or no?
No.
Still not. Okay, very good. So x2 minus 1, this is equal to x minus 1 times x plus 1. Okay, now this x plus 1, we just said that it's negative. And minus 1 is minus 2, that's also negative. And negative times negative is positive.
Oh, okay.
Good, that's why x2 minus 1 is positive. Good?
Okay. Yes. Thank you.
It's not difficult, but you just have to take time to do it and go into the details. That's it. And slowly. Okay, you have to be patient and do it. Okay. So if I'm approaching, so this, I'm just going to put a little bubble here to show that it explains this. There you go. So if I approach -1 from the left side, it's going to positive infinity. And -1 from the plus side, it's going to negative infinity. So like this. Okay. So these are for my two vertical asymptotes.
What would happen if the limits existed?
If it existed,
Yeah.
or like there's no, it wasn't infinity. That's what you're saying? For
Yeah,
example,
no,
limit was 2,
like they're equal, like plus infinity and plus infinity.
then no problem. You would have, if both of them were plus, you would have like this.
Okay.
Okay. Good. What could happen? I thought your question was something else. What could happen? What if it's 2 and 2? Okay. Then in that case, you would have something like this.
A jump.
Or a hole. If both are 2, you would have a removable.
Okay.
Okay.
I have a question. So
Yeah,
basically,
sure.
whenever you're evaluating like a negative number and you're like looking at it from the left side, it will always be the opposite. So it will always be positive.
I don't know.
It's not
Not
like the
necessarily. It depends on the case.
Okay.
Okay. You mean like because it was -1 from the left, so minus plus, something like this?
Well, yeah, like I don't know. Is it consistent like that?
No. What if it was here 1 minus x2? If this was 1 minus x2, it'd be the opposite. No, you can't say that. You really have to try it. You have to do this little logic here. That's what you have to do.
But how did you do that, like without going through that whole process? Like, how did you know? Just like plugging into the formula.
Okay, good. What I did, I went, so x is a bit less than -1. So for example, -1.5. Okay, and if I plug in -1.5 here, I'm going to get 2.25 minus 1. I'm going to get a positive. That's it.
Okay, perfect.
Okay, of course, -1.5 is way too far from -1, but it's just to get an idea of the sign. That's all. Okay. Okay, so these are my two vertical asymptotes. I have one at -1, I have one at 1. Let's do now the horizontal asymptotes. Okay, so how do you find the horizontal asymptotes? You know?
When x approaches infinity.
Very good. So I have to limit when x approaches infinity of my function, and also when it approaches, of course, negative infinity. I have to do both sides, right? Let's go. Let's do these limits. So now we have L'Hopital's rule, so it should be really fast. So limit x approaches infinity of x2 over x2 minus 1, and then limit x approaches negative infinity of x2 over x2 minus 1. You could do L'Hopital's rule, you could do or whatever method you want. Limit x approaches infinity of 2x over 2x, that's 1. And then that's limit x approaches negative infinity of 2x over 2x, and that's 1 also. Questions? So if I'm to represent what I just found here, there we go, horizontal asymptote. So I have no idea what the function looks like, but one thing that's for sure is that at infinity, it's getting close to 1, and here also it's getting close to 1. Okay, what happens in between, I don't care. I know there's asymptotes at -1. It can't cross -1 and 1. Okay, but this is what it's getting close to. And this is for my asymptotes. Any questions?
I have a question for like L'Hopital's rule.
You sure? Yeah.
If it were minus infinity over infinity, can we still use the rule?
Yeah.
Okay, thank you.
Okay, can I keep going? All right. Let's go. Let me take another page. Yeah.
I'm not done yet.
Oh, okay. Go ahead. Let me know when you're done. So the
Sure,
next
that's
step, yeah, sorry.
Why is the function above the asymptote and not under?
Oh, I don't know. Okay, it's a rough sketch.
But,
Doesn't
but
mean
it could be,
anything.
could
Okay.
it be under also? Like,
Of course, of course.
okay.
I have no idea what it looks like. Okay, or it could even be like this. If I want to exaggerate, it can even be like this. Look, it can even be like this. You understand? It could get closer and closer, even up and over, under, over. You don't know.
Okay.
As long as it getting close to this asymptote at infinity.
But it's allowed to touch this asymptote.
Yeah, that's a
Okay.
good point. So the horizontal asymptotes, you could always cross them, but not the vertical. Very good.
Okay, okay.
Okay. Okay, can I go? Any other questions? Okay. So at this point, let's find the derivatives. Okay, so this is going to be a bit more annoying because now there's a quotient rule involved. Okay, so derivatives. So let's remember that f of x is x2 over x squared minus 1. So let's find f prime. Okay, so I'm going to do the quotient rule right away. So 2x, derivative of top times bottom, minus the top times the derivative of the bottom, and all this over the bottom squared. Okay, so let's simplify what we can here. So it's 2x cubed minus 2x cubed is out, so I have negative 2x over x2 minus 1 squared. Okay, and now we're going to find the second derivative. So I have to derive this. So derivative of top times bottom minus the top times the derivative of the bottom, which is 2 times x2 minus 1 times 2x. And all this over the bottom squared, which is x2 minus 1 power 4. Questions? Okay. I'm just gonna fix this a bit because I'm gonna have to use this to find potential inflection points. Okay, so let's simplify this a bit. So the first thing I could do is I could extract an x2 minus 1 here and here. And I could, okay, I'm gonna extract, I'm gonna do it in 2 steps, okay? I don't wanna mix you up. So x2 minus 1 times, so here I have -2 times x2 minus 1, and then here I have minus 8x2 plus 8x2. Okay, and on the bottom, x2 minus 1 power 4. Okay, I'm going to pull out a 2 here. Let's pull out a 2. Actually, I could even simplify one of these. Okay, and pull out a 2 from here, from the inside. So what's left here? Negative x2 plus 4x2 is 3x2. And then -1 times -1 is +1. And all this over the bottom, which is x2 minus 1 power 3. Okay, so let me just write, I'm going to write down my 2 simplified derivatives here because I'm going to use them. So in summary, we have f prime of x is -2x over x2 minus 1 squared. And then f prime prime of x is 2 times 3x2 plus 1 over x2 minus 1 power 3. Questions? Okay. So now let's find my critical numbers. Okay, so as you see, it's a long problem, right? Critical numbers, as usual. This is when f prime of x is 0 or f prime of x does not exist. Okay, so my derivative, you see it right here. So when is it 0? So f prime of x, if x is 0, that's my critical number, one of them. And then f prime of x does not exist if what? If the denominator is 0. So basically, x equals 1 or x equals -1. These are critical numbers. Obviously, the derivative doesn't exist at 1 and -1 because we have an asymptote there, right? You can't derive on an asymptote, of course. The function is not even defined there. Good? Okay, so from here, I could find my critical point. Right here, I have a critical point, which is 0. And if I plug 0 into the function, I get 0. I have a critical point at 0, 0. And here, of course, there's no point because the function is not defined at 1 and -1. There's no point there. Question? Okay. Let's find the inflection points. These happen when f prime prime of x is equal to 0, which means when this is 0. So 2 times 3x2 plus 1 over x2 minus 1 cubed is equal to 0, which is when the numerator is 0. So basically when 2 times 3x2 plus 1 is equal to 0. And of course, this is not possible because this is always a positive number. This is always at least 1, right? It's 1 plus a positive cannot be 0. And times 2 obviously cannot be 0. So there is no inflection point here. Okay, so impossible. Good. Okay. Now we have to do the sign table, and then we're almost ready to draw. So sine okay. Let's go. Let's go a bit more space this time. Okay, so let's put my important values that I see are 0, 1, and minus 1. These are the values that I see. Okay, so 0 and then minus 1. So and 1. Like I did before. Each of the critical numbers, okay, I will put a line. And then I will, yeah, excuse me?
We don't need to put a second derivative because there's nothing to put.
Yeah, but there are still two values where the second derivative doesn't exist. So maybe there it's going to change concavity.
Okay.
Okay. So let me write it down here. Derivatives here. So f of x, f prime here, we said was negative 2x over x squared minus 1 squared, and f prime prime of x is 2 times 3x2 plus 1 over x squared minus 1 cubed. Okay. So the first derivative becomes 0 at 0, right? At x equals 0. And it is forbidden. It doesn't work. The second derivative doesn't work when x is minus 1. So I'm going to put an x here, and x is 1. Doesn't work either. Okay. Second derivative, there is no place where the derivative is 0, but it doesn't exist at minus 1 and 1, right? The function is not differentiable there. Okay, let's see what the sign of f prime is when x is less than minus 1. Okay, so when x is less than minus 1, basically when x is negative, well, the bottom is always positive, so I don't care because it's power 2. So I don't care about this. And so I just look at the sign of the top. So if x is negative, well, the derivative is positive. Here also, between 0 and minus 1, it's still negative. So still positive because minus is plus. And anything above 0 will turn the derivative, sorry, into a negative number. Negative, negative. Good? Okay. So this means that it's increasing, increasing, decreasing, decreasing. Let's go. Same thing for the second derivative now. So we just look at the bottom because the top is always positive, as you see. So if I plug in negative 1 at the bottom, negative 2, so it's going to be positive. If I plug in anything between negative 1 and 1, for example, 0, anything there, I get negative. And anything above 1, I'm back to positive. Concave up, concave down, concave down, concave up. Okay, let's do my graph. So increasing, concave up, so it's like this. Increasing, concave down, so it's like this. Decreasing, concave down, it's like this. And then decreasing, concave up, it's like this. Let's go, let's draw. Let's sketch the graph now.
Sir, could you just go up a little, please, for a second? Thank you.
Okay. Okay, let's draw. 1, 2, minus 1, minus 2, 1, 2. Right. Oops. Okay, so 1, 2, minus 1, minus 2, 1, 2, 3, minus 1, minus 2, minus. Let's go. First thing I'm going to do, of course, is I'm going to draw my asymptotes. So I have an asymptote at x equals 1. And an asymptote at x equals minus 1. Then I have a horizontal asymptote at x equals 1 as well. Okay, let's sketch the graph. I think I could leave both in the screen. Okay. So we have my x-intercept and my y-intercept is 0, 0. This I have. And then I know that my function is increasing from negative infinity until minus 1. It's increasing, and if you remember from the asymptotes, hold them back up. Okay, so at minus 1 here, it's getting close to the vertical asymptote. From the left side, it's going up to plus infinity. So it's getting close here, and it's increasing concave up, and it's getting close to 1 here at minus infinity. So it's clearly like this. Okay. Then from minus 1 until 0, it's increasing concave down, has to go to 0, and of course it's getting close to the asymptote. From the left side, it's getting close to minus infinity, like we said right here. Okay, then decreasing concave down, so here it goes. Then on the right side of 1, plus infinity, and then it's getting close to 1 on the right side as well. And this is what my graph looks like. Okay, so it's not really, it should be a bit more symmetrical. So maybe fix this here a bit because it's pretty ugly. A little better. That's it. This is my graph. So there's absolutely no inflection point, okay? Because there's no place where it changes concavity. The only places where it changes concavity from concave up to concave down is through an asymptote, so through a place where it's not differentiable. And the only interesting point we have is 0, 0, which is what is it? It is an x-intercept. It is a critical point. And it is what?
Y-intercept.
Oh, yeah, okay, y-intercept, I forgot. What else?
Maximum.
What kind?
Relative.
Very good. So relative or local, same thing. Local max, perfect. Okay, so all this is what we could say about 0.00. And that's it. There's nothing else to say in this about this curve, okay, other than the y equals 1 is the horizontal asymptote, and vertical asymptotes x equals minus 1 and x equals 1.